Okay, so permutations. We had 5 unique colors, right? They're all different. We can tell they're different. They're different, colors. We got orange, we got pink, we got blue, we got green, we got yellow, and so you can tell that they're all apart. That would be different than the case where maybe one of them, or at least one of them, was the same. So, like for instance, if I threw in another yellow in here, now we would have 2 of them that are identical, right? So we'll cover that in a little bit. But for now, we're going to stick to unique colors. So we have 5 unique colors in my pool, and let's say I want to choose 3 out of the 5. So I can randomly reach in here and pick out, say, the blue one to be first. And then I can randomly choose the orange one to be second, and then maybe randomly pick the green one to be next, right? And then we leave these alone. We're picking 3 out of the 5. Okay, so this is one option of the many, many, many options that can happen out there. Say I grab them again, and I randomly choose, and this time I pick the orange one to be first, and then the green one to be second, and then I choose the blue one to be third. So even though I ended up choosing the same color palette, because they're in a different order, this counts as a different type of selection, right? Order matters in this case. Orange, then green, then blue. Okay, so take it back and then randomly pick another one. Maybe this time I pick the pink one to be first, and then maybe I pick the blue one to be second, and maybe I pick the yellow one to be third. Right, here's another choice, right? So how many choices are there? We covered this yesterday. This is a case of permutations. We have 5 choose 3 permutations, right? 5 to choose from, right? The pool has 5. We're going to choose 3 of them, right? So we know there should be 5 options for the first one. Then there's 4 left. So then now there's only be 4 options for the next one. Then there's going to be 3 left. So there's going to be 3 options left for the third one. So it should be 5 times 4 times 3. 5 times 4 is 20, times 3 is 60. There should be 60 options total, right? Okay. But what we want to do is, so let me write those down, and I'm trying to write down the sample space of all of these. Of course, I'm not going to be able to write them all down, but I want to at least kind of get the pattern going. All right, so let me write that down. Okay, so we're still in Chapter 5, Section 5. It's a very challenging section with lots of concepts on there, so we're going to stay on there for a little bit. Chapter 5, Section 5 still, and we're still talking about permutations. Right. So the example I had was 5 unique markers. Choose 3. Right. Of course, the order matters. Okay. All right, so let's create our sample space, or at least let's begin creating our sample space. We know we had the yellow one, we had the green one, we had the blue one, we had an orange one. So, you know, my yellow and my green are going to look similar if I do it like that. So let me write green with a G this way. So yellow, green, blue, orange, and pink. So here are the unique markers, 5 unique markers. Unique markers. Okay, and then I was choosing 3 of them. So like maybe, for example, I would choose the green, the yellow, the green, and then the blue. That could be one choice. Or maybe I could choose the orange and then the pink and then the yellow. Could be another choice. Or maybe I could choose the pink and then the blue and then the orange, right? So here are various choices. So I'm just writing them all down. I'm trying to create my giant sample space here, like this, right? All the possible options that can happen. I'm also going to write them down in this way. And the way I'm going to organize them in this way is that once I've chosen a particular choice of colors, I'm going to think about all the different ways in which there are to rearrange these and keeping the same colors, right? So one case would be that the yellow is first, then the green, then the blue, in this order. These colors in this order. On the other hand, I could just keep the same colors and think about how to move them around. So I could then maybe create the blue first. You know what? Actually, let me organize in a slightly different way. Come on. Okay, so I could do yellow, then the blue, then the green. Or I could do blue, then green, then yellow. Or I could do blue, then yellow, then green. Or I could do green, then blue, then yellow. Or green, then yellow, then blue. Okay, so the way I organized them was that I wrote down all the cases in which yellow is first, here and here, and then just switch these two around. Then I wrote down all the cases where blue was first, right, and then switch those around. Then the cases where the green is first, and then switch those around. Okay, so once I've chosen these three colors in particular, the yellow, the green, and the blue, there are in fact 1, 2, 3, 4, 5, 6 different ways that we can move around these three colors, right? In the case of permutations, these are all unique cases. Good. Okay, next I can go, okay, well, maybe the case is that I first pick an orange, then a pink, then a yellow. Good. So, or, okay, let's keep track. The other case where the orange could be first could be orange first, then yellow, then pink. In permutations, these are two different cases. Okay, or maybe I start with a yellow, then I do an orange, then a pink, or I do a yellow, then a pink, then an orange, or let's do pink first, then orange, then yellow, or pink first, then yellow, then orange. Right, so here's all the ways to move around these three colors. Well, if you think about it, this goes back to our very first type of scenario where we have a complete rearrangement of three things, right? A complete rearrangement of three things. We have three items. We want to think about how many ways are there to move these things around. Well, for the first one there's going to be three options. It could be the P, the B, or the O. Three ways to put that first one. Then once you've selected one of them, like let's say I pick the P, then there'll be two options left. So then there's two ways to pick the next one. So let's say I randomly pick the O, and then finally the last one, right? One way, whatever's left. In this case, the B, right? So we know from our complete rearrangement that this should be equal to 3 times 2 times 1, which is equal to 6. That's why there are 6 ways, six ways to move around these three colors. 6 ways to rearrange and move around, to completely rearrange three unique colors. To rearrange three unique colors. Okay, good. So 6 ways to move three unique colors, and then that 6 comes from, just put it on here, that 6 comes from the multiplication of 3 times 2 times 1, right? Because there's 3 unique colors. How many ways are there to move them around? 3 times 2 times 1. Good. Okay, let me finish off this table then. So here I was talking about how many ways are there to move around the pink, the blue, and the orange. When the order matters, well, this is one way. Here's another way, and I know that there's going to be 6. I wrote down both ways in which we can start off with the pink. Now let's start off with the orange. Orange, then pink, then blue. Or orange, then, well, I took up a lot of space here, so now it's going to be, my table is going to be kind of ugly. orange, then blue, then pink. Next, let's think about all the ways in which blue could be first. So blue, then pink, then orange, or blue, then orange, then pink. Okay? All right, so if I create this giant table of all possible ways to select 3 out of 5 of these colors, 3 markers out of 5 of these markers when the order matters, then I would create this ginormous table, right? Go down this way like that, and then across this way. And I know that all of them would represent permutations. Now, we already know what the answer is for permutations, right? So permutations, this would be permutations of 5, choose 3, which is the same thing as this notation, a giant P with a little 5 there and a little 3 there. We know our formula for this is going to be equal to 5 factorial over 5 minus 3 factorial, which is the same thing as 5 factorial over 2 factorial, which is the same thing as, if we multiply this out, 5 times 4 times 3 times 2 times 1, all over 2 times 1. Now the 2 and the 2 cancel, the 1 and the 1 cancel, and so the only thing that survives is this 5 times 4 times 3. 5 times 4 times 3, which when we multiply equals to 60. Right? So we already knew that the answer is 60. There are 60 ways for us to select 3 out of the 5 markers when order matters. So this giant table here that shows you all the actual answers, right? So permutations, when you do a permutation, it only tells you how many ways there are to do something. It doesn't actually spell them out for you, right? But what I'm attempting to do here is to spell them out. What are they? Okay, so I know that this whole thing, all of this, should be equal to 60 items, right? All of this has 60 selections, 60 items, 60 outcomes. And all 60 of those can be rearranged, can be organized in this table here, where I put the unique colors in this direction, and then once I've chosen 3 unique colors, then I can figure out how to move them around, move them around, move them around, and I know that in this direction that it's going to have 6 different ways to do that. Okay, so if the whole thing is 60, here, let me see if I can create a little table here. I've made it really ugly, so I don't know if this is going to be better, but we'll try. You know what? I need to move space. So let's say I have a giant table like this, and I have 1, 2, 3, 4, 5, 6 different columns like this. Good, 6 different columns. Good. And then in each column, going down this way, I'm going to have some number, I don't know, some number. Should we use good old X calculus? Okay. So for example, this is O, orange, pink, blue, right? Or maybe it's pink, yellow, orange. Good. Or maybe it's yellow, orange, blue. Or maybe there's a green in there. Green, orange, yellow, right? So what I'm doing here is I'm choosing unique color choices. And then going across this way, I'm going to write down all the ways in which I can mix around those colors when the order matters, right? So I'm just reorganizing the same table I had before. I want to know how many unique color choices are there, and that's X. X represents the number of unique color choices. Good. Whereas this is once you've made a choice of your colors, then how many ways are there to move them around? Does that make sense? So over here, I would put a BPO because I'm just moving these around. I would not put BPO over here because that BPO is a blue, pink, orange, and I've already selected those colors, right? That same color palette over here. So I just want to organize it in a way where going in this direction is all the ways in which we can choose unique color choices. Once we've made that, then we go across this way and find out find out how many ways there are to move them around, right? And we already know that there are 6 ways. So there's BPO, BOP, OBP, POB, and PBO. There are 6 ways. Now we also know that in a giant table like this, if we want to know how many items are in there, we multiply the number of columns by the number of rows, right? So this whole thing, this whole table here, the table should be equal to 6 times x, right? The number of columns, the number of rows. But we also know that the whole thing should be equal to 60, right? From permutations. So let me put this over here. Go away. This is the number of columns, number of columns, number of rows. Good. And then this, well, I know the entire table is the permutations. This is permutations of 5, choose 3. Good, 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 good. Now the number of rows in our case was also equal to the number of unique colors when the order doesn't matter. Number of unique colors when order doesn't matter. Does not matter. Good. And also this 6, remember this 6 came from how many ways are there to mix these around when the order does matter. And because there were 3 colors, we knew that this was equal to 3 times 2 times 1. That's how we got that. Good. Which is the same thing as 3 factorial. Good, 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 good. Okay, so the reason the place I'm driving to here is that we want to find out a formula to figure out how many ways are there to choose unique colors when the order doesn't matter. And that's what this is. The number of rows here will tell me how many unique color combinations are there when order doesn't matter. And it's hard to figure them out on your own when you have, 5 colors in a set of markers. How many ways are there to pick the colors with the order not mattering? And the way we do it is that, in fact, first we figure out the permutations, because that's easy. And then we divide away the number of columns here, the number of ways to mix them around, right? It's sort of the excess amount. So if we divide both sides here by the 6, we get a value for x. Good. So we want to say that the 3 factorial, so from here we can get that this is the same thing as 3 factorial times x. Now x is the number of ways to choose the colors. That's what we're after. And this is equal to permutations of 5 choose 3. This is the 60. So therefore x, the number of ways to choose the colors with order doesn't matter, is equal to the number of ways to get the permutations divided by 3 factorial. Good, good, good. So this is called combinations. 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 right? So given n, oops, given, well, I'll just do it for this one. Given 5 unique markers, there are P choose 5, 3. So 3 choose 5. So out of permutations of 5 choose 3 divided by 3 factorial, right? So this number, there are this number of ways to select 3 markers when order does not matter. Good. Okay, so how do we simplify that? Let's work on simplifying that. Well, from here we could see that it's just going to be 60 divided by 6. Right? Permutations of 5 choose 3 is equal to 60. But let's follow the formula. So the formula for permutations is 5 factorial divided by 5 minus 3 factorial. Right? That's the permutations part, divided by the 3 factorial. Okay, so this is going to become 2 factorial. This is 5 factorial divided by 2 factorial divided by 3 factorial. Good. And now we have a giant fraction where the numerator itself is a fraction, right? So this guy is a fraction. And we can think of this as a fraction if we put a little 1 underneath it. So how do we simplify a giant fraction where the numerator is a fraction, the denominator is a fraction? We multiply the numerator times the reciprocal of the denominator. So we'll end up with 5 factorial over 2 factorial times 1 over 3 factorial. Good. Okay, so this simplifies into 5 factorial over the product of these two, and we can leave it as 3 factorial, 2 factorial, like that. Good. Well, this part right here is exactly this part, which was the result of that. So we can rewrite it all this way. Too far this way. We can rewrite it all as 5 factorial over 3 factorial over 5 minus 3 factorial, just the way it was before. And we've arrived at what the formula for combinations. This is going to be the formula for combinations. So notice that it was, we were choosing, we had 5 to choose from, 5 markers to choose from in pool to select from. And we were going to pick 3. Pick 3, right? So the numbers that we're working with is 5 in the pool, pick 3. And look at our formula. It's going to be the 5, which is the total in our pool, and then we're picking 3, and there's a 3 there, and there's a 3 there, right? So this is the formula for combinations. Pick 3, and this is the case where we pick 3 and order when order doesn't matter. Order does not matter. Good. Okay, so we will revisit this. Oh, let's just do it right here then. So now in general, say we had n markers, right? Some total pool in our population. We have n markers to choose from. In general, n unique markers are given. markers are given. How many ways are there to choose from? How many ways are there to pick R markers when order doesn't matter? Right? Order does not matter. Okay, well, we can just follow this little formula from here. When we did it with 5 and 3, we ended up with this guy. So just kind of mimicking it, we would get that the answer is going to be, instead of a 5, we have an n. That's the total to choose from. So it'll be n factorial divided by, and then the 3, that's how many you're picking, right? So that would be the r. So there's going to be an r factorial here. And then we have a 5 minus 3, right? Sort of the difference, the one's not picked. So that'll be n minus r, parentheses, factorial. Good. So n is how many you have to choose from, r is how many you're picking, and n minus r is the ones left behind that didn't get selected, right? If you had a total of 5 and you're choosing 3 markers, that means that 2 of them don't get picked. So it's actually not a bad formula to remember without really memorizing this whole thing. You could just say the total number that you have to choose from divided by these 2, and this is the number that you pick, and then the number that you don't pick. Good. We call this combinations, so we like to use this giant C, and we put a little n there to say how many are in the pool to select from and how many you're choosing. So this is combinations of n choose r. Good. So this is combinations of n choose r. R. Good. Good, 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 good. Maybe, sort of, kind of, maybe. Kind of, maybe. Okay, let's do another example. And we'll do both permutations and combinations to, again, figure out what the difference is between them. So let's go to another page over here. So for example, okay, let's go back to our markers and let's throw in one more in there. Let's throw in a black, a green, a purple. Let's make it crazy numbers now. So let's say I have, okay, so now let's say I have all of these, and I have a green highlighter, yellow, orange highlighter. Then I have also a purple marker. Actually, I have a lime green marker. Actually, I don't like this one. A lime green marker, a yellow highlighter, a pink highlighter, a black marker, a blue highlighter, and then a blue marker. So there I have these 1, 2, 3, 4, 5, 6, 7, 8 different ones. If I wanted to figure out how many ways are there for me to rearrange, a complete rearrangement of all of them, right? Just mix them all up and then, put them all back down. There's 8 of them. And so we know that was the first type of thing we did. The first type we worked with was a complete rearrangement. So there are 8 options for the first one, right? There's 8 options that can be selected for the first one. Now there's only 7 markers left, so now there's 7 options that can go for the next one. And now there's 6, and so you keep going, right? So it's going to end up being a countdown. A complete rearrangement is going to end up being a markdown of 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? That whole multiplication will tell you how many ways are there to completely rearrange them all. On the other hand, if I had 8 and I was choosing 4 of them, 8, choose 4, and let's say I care about the order. So if I care about the order, that means that there are 8 ways to choose the first one, then 7 ways to choose the next one, then 6 ways to choose the third one, and finally 5 ways to choose the next one. Right? So there's still going to be 4 left over in my hand, and here's one choice. Now with permutations, the order does matter. So this is one selection, but if I grab them all and then I put them all but like in a different order, let's say this order here, then this would be a different choice. Right? So this is permutations of 8, choose 4. On the other hand, if I just want to know how many different color options are there, right? They're all unique markers. How many ways are there for me to choose 4 unique markers, say these 4, when the order doesn't matter, right? They're just in some little combination. It could be these guys like this. So maybe I choose these guys. Again, the order doesn't matter. Or maybe I go in here and I move them around, and maybe I choose these 4. Right? So again, the order doesn't matter. I just want to know how many ways are there to make a selection of 4 out of the 8 markers. So that would be combinations. That would be combinations of 8, choose 4. Okay, so let's write that down. Okay, so we had another example where we had 8 markers, 8 unique markers. And the first one was, how many ways are there to completely rearrange them all? There are 8 factorial ways, 8 factorial number ways. Well, there are. There are 8 factorial equal to, let's just figure out what that is. If you get your calculator, you remember where we use factorial from last time. That would be 40,320. 40,320 number of ways to completely rearrange all 8 markers. Obviously, the order matters, right? Because we're lining them all up. So that should go without saying. B, okay, what if I just wanted to pick 4 out of the 8? What order matters, right? So there are, and this is permutations. So it would be permutations of 8, choose 4, right? Permutations of 8, choose 4, following our formula, that's 8 factorial divided by 8 minus 4 factorial, which equals to 8 factorial divided by 4 factorial, which is going to end up being 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. All of these guys cancel. So really I just end up with the multiplication of equals the multiplication of 8 times 7 times 6 times 5, which then I can go to my calculator. Away. So I can go to my calculator and do 8 times 7 times 6 times 5, and I get 1,680. 1,680. Or I can use the button for permutation. So we covered that last time, but I might as well do it again. So let's do the button for permutations. Permutations. Oh, so it's still remembering from last time. But okay, so 8 times 7 times 6 times 5 is equal to that. Or I can hit 8, math, go over to where it says probability, and then go down to where it says NPR, permutations of N choose R. And we're going to choose 4 of them. Enter. So we get the same answer, right? So it makes it a little easier. So there are 1,680 ways to choose 4 out of the 8 markers when the order matters. Good, so let's put that aside. Let me restart the sentence there. There are 1,680 ways to select 4 out of 8 unique markers when order matters. Good. And then finally, the last thing we looked at was this new thing, combinations. C, combinations. How many ways are there for me to choose 4 out of the 8 colors when the order doesn't matter? And that's what we call combinations. Combinations of 8 choose 4. Following the little formula we came up with, there should be 8 factorial over 8 minus 4 factorial. So this gives us the permutations, but then we have to divide the whole thing by this factorial. Right? This is the r factorial. It's r factorial, and then this is the n minus r factorial. And so this ends up being 8 factorial over 4 factorial times 4 factorial. Good. Okay, so this ends up being, well, if you expand it all out, it'll be 8 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by, well, there's one copy of this little sequence, 4, 3, 2, 1, and then another one, 4, 3, 2, 1, like this. So one of them easily reduces, 1, 2, 3, 4, 1, 2, 3, 4. And now these, well, okay, 8 times 2, 4 times 2 is 8, so that cancels out with that 8. And then this 3 reduces with that 6 to give you a 2. And so the only thing that survives all of this cancellation is a 7, a 2, and a 5. Oops. Equals, no, that's too messy. So equals, equals a multiplication of a 7 times a 2 times a 5. Well, that's 10 times 7, that's 70. 70 ways to do this. Good. Luckily, there's also a nice easy button on your calculator that we can take advantage of. So let's do that now. We want to do combinations of 8 choose 4. Right? This was permutations of 8 choose 4. This is going to be combinations of 8 choose 4. Let's go to our trusty calculator. So we will do 8 math, and then go over to probability, and then right here, the third option is combinations. Enter, choose 4. Enter, we get 70, right? So it gives us the same thing. Nice, easy button. You can use either one on the test. It doesn't matter to me whether you use this or whether you expand it all out and do it this way. Either way is fine. This isn't a class on arithmetic, so I'm not trying to force you to do it this way. I'm not trying to force you to do it this way. I'm assuming that this is something you can do, since it's assumed that everyone knows algebra already. The hard part is going to be understanding when this is appropriate and when this is appropriate, right? So based on reading the word problem, reading the questions you're working with, you have to make the decision that this is a case where permutations are applied, or this is a case where combinations are applied. Good. So the key to either one of these is that you have a pool of items to select from. The pool of items could be, could be people, individual people, or the pool of items could be social security numbers, or the pool of items could be zip codes, right? So we have some sort of pool of items from which we're going to take a given number of values, right? So we have, a computer program has all let's say it's the DMV, and so they have the driver's license numbers of everybody in California. So that's your pool, and from there you're going to randomly pick 10 of them. Okay. Now, will it matter, right? So you're going to pick 10 people, and those 10 people are going to win $1 million. Okay, do you care whether you're the first one picked or the seventh one picked? No, everyone's getting $1 million, right? So in a case like that, it's combinations, right? Because you just want to know how many ways are there to pick 10 unique people from the pool of driver's licenses, and then everybody in that pool gets $1 million. So a case like that is combinations. On the other hand, if maybe you're going to pick 10 people, first person gets $1 million, second person gets 900,000, third person gets 700, 900,000, 800,000, 700,000, 600,000, ... Now it matters. You want to be the first one picked, right? So not only do you want to be picked, but you want to be the first one picked, or you want to know how many ways are there to pick people in any given order. Right, so now if the order comes into play, there's a reason for why being first or being second is important. Well, now you're thinking about permutations. How many ways are there for me to be selected and be in a particular spot? Right, say I want to be the first one. I want to win the $1 million. Good? Good. Okay. Let's move on to this thing. All right, there's only one last thing to consider, and then we'll be done with everything, all the major concepts in this section, and then we'll just kind of recap it all, because I know there's a lot to take in. Okay, so the last thing we're going to think about is cases where some of them are not identical. So let's say, for example, that we have, let's go back to this thing. So let's say we have these, let's make them 5 again, orange, yellow, blue, and pink. So let's go back to these 5 ones, right? We know that there are 5 unique colors here. There's 5 markers or highlighters, and we want to know how many ways are there to completely rearrange all of them. That's back to basics, right? We have 5 options, 4 options, 3 options, 2 options, right? So there's going to be 5 ways to do the first one. Once I've chosen that one, there's 4 left, so that means that there are 4 ways to choose that one. And then once we have that one left, then there's 3, then 2, and then the last one, right? So there's going to be 5 factorial number of ways to move these around when they're all unique. Okay, but the twist we're going to throw is that we're going to get rid of 2 of them. Let's say I replace these 2, and I replace them with these 2. Now I have 3 that look identical, right? 3 identical markers. So now, whenever I make some moves are detectable, right? So like if you were looking at this lineup, and then you blink, and in the moment that you blinked, I move these around, you could tell that something is different. I moved these, I switched those around. So those would be 2 cases. That's one case, here is another case, right? Those would be 2 unique cases, that one and that one. However, if you blink and I make a move, some moves are not detectable. So like if I switch around the last 2, haha, look at that. And you're like, wait a minute, did you even do anything different? I did. Well, what if I move these 2 around? Look, I moved those around. You're like, did you even do anything different? Right, so some of the moves are going to be undetectable. Good? Okay, so what we want to do is think about our entire sample space when they are not identical, when they're all unique. That's 8 factorial, right? I'm sorry, 5 factorial. When I have the 5 factorial cases, that's the total pool of all possible ways when they're all unique. And from those, I want to divide away the cases that are undetectable and therefore should not be counted. So the way we're going to do that is to put maybe a little number on these guys. So put a little bit of tape. Let's say I call this one marker number 1. So now we can tell that that one is number 1. And this one, let's make it marker number 2. So now I have a marker number 2, and then I have a marker number 3. Okay, so even though they are all orange, now we can tell because of the numbers that they're, when we can detect a move. So that if I switch these two around, now I can tell because there's a number there to keep track of them, right? So we can tell that that's different. And if I move those around, again, I can tell that that's different. Good, 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 good. Okay, so let me try and write down the space all together, or at least kind of begin to write it all down in a particular pattern so that we can get the actual answer we want, right? And remember, the answer we want is how many ways are there to move these if these numbers were not there, so that some of the cases are undetectable if we move them around. Okay, all right, so let me write that down. Okay, so my experiment is going to be a complete rearrangement, right? So we were given a blue, a green, and then I had 3 oranges. 3 oranges. But for the moment, let's keep track of them with numbers. So there's orange number 1, orange number 2, and orange number 3. So at the moment, let's pretend they're all unique. Right? So how many ways are there to completely rearrange all of these? Well, there's 5 of them. So there are 5 factorial, which is 5 times 4 times 3 times 2. So that's going to be 6. Times 20, 6 times 20 is 120 ways to completely rearrange all 5. All 5 markers, taking into consideration the numbers so that they're all unique. When considering the numbers on the oranges, markers, to make all... I'm sorry, there's a question? Okay, so for example, I'm going to just begin to write down that sample space. So maybe it's a blue one, then orange 1 came in, then the green one, and then orange 2, and then orange 3. That could be one way to organize the 5 markers, right? Another way to do that could be that maybe it was the green one, and then an orange 1, and then an orange 3, and then a blue, and then orange 2. That could be another way in which we organize them, right? Okay, and then, all right, well, what I'm going to do is think about where to put the blue and the green. There are 1, 2, 3, 4, 5 different places that I can put the blue and the orange, right? So the blue could go here, the blue and the green. The blue can go here, or the green can go here. The blue can go here, the green can go here, right? And then once I've placed down my blue and my green, so let's say I put my blue, I put my blue there, and I put my green there, then the rest are orange, right? So I'm just kind of thinking about the different ways in which that can happen. Orange can go there, orange can go over there, and then orange could go over there, right? Okay, this, as I'm kind of creating my giant sample space, this is going to be kind of my columns. Once I've made a choice for my blue and my green, so let's say my blue is there and my green is there, then there's a space there and a space there and a space there, then I'm just going to move around the oranges, right? And there are 3 oranges to move around, so I could put orange 1 here, and then orange 3 there, and orange 2 there. Or I can put my blue and my green there, which means I can put my orange 2 there, orange 1 here, and orange 3 there. Or I can put my blue there, and then I can put my orange 2 there, my green, and then my orange 3 and an orange 1 there, right? Just a couple more cases. On the other hand, I could put my blue there and my green there, and then I could put my orange number 3 there, orange number 2 there, orange number 1 there. Final case, I can put my blue there, my orange number 3 there, my green one there, orange 1 and orange 2 there. Okay, so just by looking at all the different ways in which I can put a blue one in the first spot and a green one in the third spot, and then I think about, well, how many ways are there if I put one of my orange ones there, one of my orange ones there, and one of my orange ones there, right? So there are 3 ways for me to put that first orange one there, because there's 3 oranges to choose from. And then there are 2 ways to put the next orange, and finally the last orange. 1 way to do that. Good. So that's why in this direction, in this giant table, there's going to be 3 times 2 times 1, which is equal to 6. There are 6 in this direction. Good. Good. Okay. And in this direction over here, well, I'm just putting down all the different ways in which I can put the other markers that are not orange. So here I put my blue marker in spot number 1 and the green one in spot number 3. Or maybe I put my green marker in spot number 1 and my blue one in spot number 4, right? Or maybe I put my blue one in spot number 2 and the green one in spot number 3. And then just kind of think about all the ways in which I can move around all of the other ones. Okay, so now in the number of columns here, we are able to detect that something has changed even if the numbers weren't there, because we're moving around the colors that are not orange, right? If all the orange ones were, if we remove these numbers, then all of these cases here would look identical, right, to somebody who was looking at these, right? If you can't see the number, if the number was hidden, all you see is blue, orange, green, orange, orange, blue, orange, green, orange, orange, blue, orange, green, orange, orange, right? So all of these cases look identical, right? There's nothing special about them. The only time you can detect something has changed is when you move around the colors, right, from that are not orange in a different spot. So I can tell the difference between this one and this one because this one started with the blue, this one starts with the green. Right away I know something is different. Good. And then I can tell this one is different from all of those because it started with an orange, right? Different from all those other ones. Good. Okay, now the entire sample space, if I was taking the numbers into consideration and all that, we saw that that was going to be 5 factorial. There are 120 different ways for this to happen. 5. There are a total of 120 different ways for this whole thing to happen, whereas the detectable ones are the columns, right? So let's change this thing over here. These columns here will represent the number of ways that we can detect a change has been made, because the colors that don't involve the orange have been moved, right? Let's say this is the number of ways. Let's call this x. X equals the number of ways to move them, ways to select the order in a way that can be detected even if all the orange ones don't have numbers. even when the orange markers don't have numbers. Even when the orange don't have numbers, right? So I have this giant table. I know that the entire table is going to be equal to 120. Good. And I know that in this direction, this is 6. There are 6 this way. So I end up with 6 times x must be equal to 120. Good. Now this 6 comes from the fact that there are 3 factorial number of ways to move around the orange ones. The x, we said, was the number of ways to move around the other colors in a way that would be detectable by someone, even if the numbers in the orange ones are not there. That's the thing we're actually looking for, the number of ways to uniquely move them around, right? To select them in a way that can be detected by someone. Good, that's what we want. And then this one is just coming from the 5 factorial. Good. So we want to solve for x. We divide both sides by this, and we end up with the formula that x is equal to 120 divided by 6, which is the same thing as 5 factorial over 3 factorial. Good, 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 good. Then if we go ahead and divide these here, we'll end up with 20. Right? 120 divided by 6 is just going to be 20. So there's actually only 20 unique ways for us to rearrange all 5 markers when 3 of the markers are identical. Does that make sense? There are 20 ways to completely rearrange 5 markers when 3 are identical. Good, 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 good. Sort of, kind of, maybe. Okay, so then just in general then, go here. So in general then, given n items with n sub 1 one type, with n sub 1 equal the number of identical ones, of type 1, n sub 2 equal to the number of identical of type 2, and so on and so forth. So let's say that there are n sub k number of identical of type k, right? So for example, orange, this could be that there are, just to throw some numbers on here momentarily because I know this looks confusing. Let's say that we had, I don't know, 50 markers, but of those 50, maybe 7 are orange, right? 7 are identical orange. Maybe 3 are identical yellows. Maybe dot, 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 right? And then maybe the last one over here could be that there are 4 identical blue ones, right? So dot, 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 dot. So there's lots of colors. There are k number of colors, right? K colors colors. Good, 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 good. Okay, so it must be true such that n must be equal to the sum of all those markers. 1 plus 2 plus the third color of marker plus dot, 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 all the way out to that last one, right? And there are k number of colors. Good. Then there are n factorial over n sub 1 factorial times n sub 2 factorial times n sub 3 factorial, dot, 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 all the way out to that last colored marker. N sub k factorial, number of ways to completely rearrange all n markers, to completely rearrange all n markers when some of them are identical. When we have n sub 1 identical type 1, comma, n sub 2 identical type 2, dot, 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 and n sub k identical type k. Good. So if we have a case where we have lots of things that are identical, like in my case with the markers, then this formula will help us figure out how many ways are there to move them around. Let's do one more case like this one. This one's extra confusing, I think. Formula is ugly. So let's do one more case with this one. So let's say I have a few that are identical. I have a couple yellows, I have a couple oranges, and let's forget the numbers for a little bit. So we have 3 oranges, we have greens, we have pinks, purples, great. 2 greens, yellows, okay, so 4 yellows, greens, purples. Now let's go with these. That's good enough. Okay, so I have 3 oranges, I have 2 greens, 1 pink, and I have 4 yellows. Right, so of course we have 4 identical ones, the yellows, 4 identical yellows, 3 identical oranges, 2 identical greens, and then the pink and the blue are the identical. I'm sorry, unique. So total I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 total number of markers, and I want to know how many ways are there to completely rearrange them all, right? So I'll still have nothing left over in my hands, right? So for example, I could select this orange to be first, right? And then I can go into my little pool here and randomly select, and maybe the yellow one's next, and then maybe this other yellow one's next, and then this blue one, and then this pink one, and then this orange one. And then the green one, and then another yellow one, and then another yellow one, and then the green one, and then another orange one. This could be one way to do it, right? So if they were all unique, we know that there would be 11 factorial number of ways to do this, right? 11 options for the first one, then 10, then 9, then 8, then 10. However, when we take that really big number, 11 factorial, we're overcounting some cases because this is one unique way of choosing them. But now if I moved around the yellow like this, you wouldn't even notice that anything has changed, right? These two are both yellow, so just moving them around is undetectable to people, right? Same thing with these two orange ones. If I swap those two around, put that one over there and put that one over there, again, you wouldn't even notice that anything has changed. So how many ways are there for me to move around the colors that are in the same type without you noticing that anything has happened? Well, first of all, there's two green ones, right? So I can just, as long as I keep them there in these two spots, you can't notice that there's a difference. So I can put either one of these two green there and the other one there. So there are two choices. 2 times 1. Good? Okay, then looking at the orange ones, there are 3 orange ones. And as long as I keep one there, and one there, you won't even notice the difference, right? So I could take all 3 of these, and then I can pick orange one there, this orange one there, or I can put this orange one there, or I can put this orange one there, right? So there are 3 different oranges that can go there. Once I've made that choice, I have 2 left, and then as long as I pick one of the oranges here, you won't notice that there's a difference. So I can pick this orange or this orange, so there's 2 options left. And then finally the last orange over there. So it would be 3 times 2 times 1. Different ways to move around the oranges. And finally the yellow, and as long as I keep 2 there and 2 there, 2 there and 2 there, then you won't notice a difference, right? So there's 4 options to pick that first one there. So 4 options, then 3 options, then 2 options, and then 1 option. That's why we have to divide by 4 factorial. Good, 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 good. Okay, so all of that was one case, right? It should be all one case. The only way you can detect it is if it's orange, then yellow, yellow, blue. So you don't really care which yellow goes in its place. Good, good, good. All right, let me write that down then. Okay, so another example. We had 11 total markers. 11 total markers. Right, and n sub 1 was the number of yellow markers. So let's say there were 4 yellow markers. N sub 2 is equal to the green ones, and we had 2 green markers. 2 green markers. N sub 3 is equal to the green-orange markers, so that we had 3 orange markers. Then we have n sub 4 equals to 1 blue one, and n sub 5 equals to 1 pink one. And then adds up to, let's see, that's 6, 10, 11. 11 total markers, right? 11. Right, so we have that n sub 1 plus n sub 2 plus n sub 3 plus n sub 4 plus n sub 5 equals to n. Good, good, good. So that part of it matched. And so if we want to know how many ways are there to move them around in a way that's notable, that's detectable, the answer is going to be to take the 11 factorial. That's the result we would get if they were all unique and special, right? If all the yellows had numbers on them so we can tell that something has changed. So if they were all unique and special, there would be 11 factorial number of ways to move them all around. But they're not all unique. We have to divide away all these other factorials. So it ends up being divided by 4 factorial, divided by 2 factorial, divided by 3 factorial, divided by 1 factorial, divided by 1 factorial, right? We divide away the number of ways to move around the yellows when they're undetectable, the number of ways to move around the greens, to move around the oranges, and then the blue and the pink. Now 1 factorial is just equal to 1, right? And whenever we multiply anything by 1, it doesn't really affect anything. So if you wanted to, you could just kind of ignore those extra 1s there. And that looks really messy. Let me rewrite that down. We could just write it as 1 factorial and then 1 factorial like this, but these really just mean 1, so they're just kind of in the way. Just 1, 1. Good. So we could expand this whole thing out and simplify it by hand, but I think it would just get really messy. So this is something where we definitely want to use our calculator. Okay, so 11 factorial divided by 4 factorial divided by 2 divided by 3. Right, and that's just based on the colors that were provided. So let's go over to our calculator. Figure out the answer. Okay, so we want to do 11 factorial. So we got to go to math, probability, down to factorial, divided by, and now I'm going to put a parenthesis to make sure that all of this gets trapped down in the denominator. And we had 4 math factorial times, and now we had 3 math factorial times, and then 2 math probability down factorial. Close parentheses, enter, and that's what we get. Still a pretty big number, right? That's going to be 138,600. Right? This is the number of ways to rearrange all 11 markers, keeping in mind that some of those markers are identical, the yellows, the greens, and the oranges, so that some of those moves count as one, right? They're all going to count as one move because otherwise they're undetectable. Right? Now, if there were 11 unique markers, right, that would be just 11 factorial, which would be a huge number. So let's see what that is. 11 factorial is that. So there are 39,916,800 ways to move around 11 unique markers. They were all different colors. There would be 39 million ways to do that. But given that some of them are unique, some of them are not unique, some of them are identical, then that really whittles it way, way down. Good? Good, good, good. Questions, 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 questions. Okay, so let's get rid of this thing. Let's wrap it all up. I know there's a lot of stuff in Chapter 5. All right, so I know that I've been talking for 2 days about 5.5, but let's recap 5.5. So first of all, this section is on counting techniques. So we're going to look at counting problems using the multiplication rule. Then we're going to use permutations or work with permutations and combinations. We've already been doing that. And then we're going to look at cases that involve permutations with non-distinct items. So some cases where some of the items are identical, what we just finished doing. Okay, so first of all, let's look at the multiplication rule. The multiplication rule says that if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on and so forth, then the task of making the selections can be done and then what we do is we multiply all the different options for each one, right? That's what we've been doing so far. So just kind of writing it down, formalizing it. So for example, let's say that we have the fixed price dinner at Mabenka restaurant provides the following choices. We get to choose an appetizer, and we get a choice of soup or salad. Then we get to choose an entree, and we get a choice between a baked chicken, a broiled beef, pork liver, or Italian sausage. Okay, so then after that, we get to choose a dessert, and we get to choose from fruitcake or cheesecake. Right? How many different meal combinations are there? Create a tree diagram to organize all your results. So a tree diagram is something like this, right? So we have our first choice, and we have our soup, or we have our salad. Right? This is choice number 1. Option number 1 is that guy. From there, we're going to create this tree that goes over to option number 2. And for option number 2, we have 4 different things to choose from. Option number 2 is the entree, and we got a choice of chicken, right? And then beef, pork, or Italian sausage, right? So chicken, beef, pork, Italian sausage. Or, again, we gotta extend this out this way. And we have a choice of chicken, beef, pork, or Italian sausage. So someone could choose the salad first and then the pork, or someone can choose the pork and then the Italian sausage, right? Which leads to option number 2. Option number 2. And finally, we lead to option number 3, where each one of these little guys goes either to the fruitcake or the cheesecake, right? Or maybe it's the fruitcake or the cheesecake, or maybe it's the fruitcake or the cheesecake, or maybe it's the fruitcake or the cheesecake, right? So for each one of these, we have 2 options that go this way. F, C, F, C, F, C, F, C. Sorry it's so messy. But this whole, and this is option number 3 here. Option number 3. Okay, so this is a tree diagram, and what's great about this is that each one of these things leads to one choice. So it could be a soup, then the chicken, then the fruitcake. That's the first option here. This little tree branch over here leads to soup, then the cheesecake, then the chicken, then the fruitcake. Good. This option there leads to the soup, then the chicken, then the cheesecake. Good. Then this option here leads to the soup, then the beef, then the fruitcake, right? And so on and so forth. So each one of these things represents the outcomes. So a tree diagram is a great way to write them all down. If you were asked to list them, or if it was important to list them all down, we can do it this way. The great thing, though, in statistics is we very rarely actually need to write them all down. We very often just need to know how many are there total. Okay? And how many are there total comes as a multiplication of the number of options available to each one. So the first choice you make, there were 2 ways to choose that. It was either soup or salad. The next one, there were 4 options to choose from: chicken, beef, pork, or Italian sausage. And then finally, the last one, there were 2 ways to choose that. Okay, so 2 ways to make that first choice. Then there's 4 ways to make that next choice. And then finally, there was 2 final ways to make your third choice. So we end up having this multiplication of 2 times 4 times 2, which ends up being equal to 16. Good. There are 16 total options, and if we count off these branches here, we'll see that there will be 16. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Good. So if I just want to know how many ways are there, I could just multiply the number of options available for each of the choices I have to make, and then that will tell us how many there are total. On the other hand, if you're asked to write them all down, or if it's important to write them all down, then a tree diagram will help us do that, to figure them all out. Okay. Any questions about tree diagrams? No? Okay, so that's what they say here. Ordering such a meal requires 3 separate decisions. Choose an appetizer. For each choice of an appetizer, we have 4 choices of entrees. For each of these 8 pairings, there are 2 choices for dessert. So we have a total of 2 times 4 times 2, or 16 different meals that can be ordered. Okay, next we introduce factorials, right? So for us, n is going to be a positive integer, and it represents a countdown multiplication. We've been working with these for the last couple of days already, but just to make sure. For example, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1, right? By default, 1 factorial means it's just a 1, and 0 factorial might not be so intuitive, but we define it to be this, right? It just makes sense in math to define it that way. So that's just one thing we have to memorize. 0 factorial means 1. Okay, next we got into permutations, right? So permutations was when we have n items in a pool. They're all unique, they're all special, and we want to choose R of those items, right? A permutation is an ordered arrangement in which R objects are chosen from n distinct objects so that R is less than or equal to n, of course. R is the smaller number because we're choosing from n of them. And repetition is not allowed. You're never allowed to pick the same one more than once, right? So the symbol, this giant P with a little n and a little r, the way we read it is to begin with the giant P and say permutations. So this is permutations of R objects selected from n objects, or the other way around of saying permutations of n choose R. So either way is fine. So P, right, the way I like to read it is permutations of n objects choose R. Of n objects choose R. Or the other way around, sentence permutations of R objects selected from n. Good. Okay, so we've been working with these already, just kind of formalizing it. So the number of arrangements of R objects chosen from n objects in which the n objects are distinct, they're all unique, we can tell them apart. Like in our examples with the markers, we have all n unique colored markers. Repetition of the markers is not allowed, meaning that we're not allowed to pick the same marker more than once. Right? We're picking them and line them up. Order is important, and we saw that our formula is this one, permutations of n choose R. And it's n factorial over n minus r parentheses factorial. Here's an example. In how many ways can horses in a 10-horse race finish first, second, and third? Right? So how many different outcomes can there be? And obviously, order is important. So this is going to be permutations of 10 choose 3. Permutations of 10 choose 3. There are 10 unique items to choose from. We're going to be picking 3 of those items. And so following the formula, this is 10 factorial over 10 minus 3 factorial, which is going to be 10 factorial over 7 factorial, which reduces to 10 times 9 times 8 times 7 factorial, right? Because this means the rest of the countdown of 7, 6, 5, 4, 3, 2, 1 divided by 7 factorial. And so now this is a new way to, a new shortcut for this. We can simplify it this way. Good. So 8 times 7 is 72, times 10 is 720. There are 720 different ways in which the horses can come in first, second, third. Good. Questions, 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 questions? Right? 720 different ways. Okay, combinations. A combination is a collection without regard to order in which R objects are chosen from n distinct objects with R less than or equal to R without repetition. So the same one cannot be selected again. So again, with our markers, we have n unique markers. They're all different colors. And now we want to know how many ways are there to pick R of those markers when the order in which we pick them doesn't matter. Okay, we just want to know how many color combinations are there without really paying attention to the order in which they're selected. Okay, so this is the number of combinations of n distinct objects taken r at a time. So we have n objects that are distinct, unique, like n different colored markers. Repetition of the objects is not allowed, meaning that as you're selecting them, you cannot select the same color more than once. Good, so you can't repeat the same color. And the order in which you select them does not matter, right? So with permutations, the order does matter. With combinations, the order does not matter. And so we saw that this is the formula for it, right? So combinations of n choose r. Here's an example. How many different simple random samples of size 4 can be obtained from a population whose size is 20, right? So we have 20 individuals, and I want to say 20 people in my class, and I want to pick 4 of them, and those 4 people have to take a quiz. Everyone else gets to go home. Or, well, I guess if you're in a classroom. So 16 people don't have to take the quiz. 4 people are going to be randomly selected, and they will be quizzed. Okay, so in this case, the order doesn't matter, right? Because you don't really care whether you're the first one picked, the second one picked, the third one picked, or the fourth one picked. Either way, you got to take a quiz. Right? So that doesn't matter. So how many different ways are there for 4 students to be picked from a pool of 20? Right? So 20 individuals in the population are distinct. In addition, the order in which the individuals are selected is unimportant. Thus, the number of simple random samples of size 4 from the population of size 20 is a combination of 20 objects taken 4 at a time. Right? So the answer to this is combinations. Combinations of 20 choose 4. Good. Following our formula, that's going to be 20 factorial over 20 minus 4 factorial, and then there's this extra 4 factorial in there. Good. So this is going to be 20 factorial divided by 16 factorial, divided by 4 factorial, 16 factorial. So this is going to be 20 times 19 times 18 times 17 times 16, 15, 14, right? So the rest of it I can just write down as 16 factorial. Now this one I'm going to go ahead and expand. That's going to be 4 times 3 times 2 times 1. But the 16 factorial, I'm just going to leave it alone because I can see right here that it cancels with that one. Easy. So now it makes it a little easier to reduce some of these things. The 2 and the 18 reduce, giving me a 9. And the 4 goes into 20, giving me a 5. And this 3 and that 9 reduce, so I'll cancel that guy, giving me a 3. So the only thing that has survived is a 5, a 19, a 3, and a 17. The combinations of all these things is going to be 5 times 19 times 3 times 17. Good. So we can multiply that out, and we get 5 times 19 times 3 times 17. So I get 4,845. Or we can go to our calculator and type that in as we've done before and confirm that we get the same result. Okay. So here's our formula. Plugging it all in, we get 4,845 different simple random samples of size 4 from the population of 20. So I have 20 unique students in my classroom, and I want to pick 4 of them at random to take a quiz. Obviously, the order doesn't matter in this case, just 4 people. There are 4,845 different ways in which that can happen. Okay, permutations with non-distinct items, right? The one we just did. The number of permutations of n objects in which n sub 1 are of one kind, n sub 2 are of a second kind, and so on and so forth, until we have the last kind, which is n sub k. So there are n sub k. There are k different types running around in our population, right? So with the markers, for example, we could say that n sub 1 are like the yellow markers. N sub 1 is like the yellow ones. and n sub 2 is like the orange ones. Right? Maybe there's some that are identical orange and some that are identical purple, and so on and so forth, right? So there are k colors running around. Good. And then if we add up all the yellow plus all the orange plus all the purple plus dot 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 dot, gives us all the markers we have total. Good. Okay, so the number of ways to completely rearrange them all when some of them are identical is this formula that we worked with before. Okay, so let's do another example involving those. How many different vertical arrangements are there of 10 flags if 5 are white, 3 are blue, and 2 are red? Right, so this is from World of Ships, right? So if we had a giant pole like this, and we have these little flags that they put on ships so that you can, kind of send messages back and forth from really far away. Back before we had radios, people didn't know how to communicate from one ship to another ship. So what they would do is just put up flags. So we're working with the colors white, blue, and red. So maybe this is a white one, this is a blue one, this is a white one, this is a red one, like this, and maybe another red one. Right, so there's 2 red, there are 3 blues, so there's a blue one there, another blue one there. Right, how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's toss another one up here. Like this. 1 blue, 2 blues, 3 blues. Let's put the blue one there. And there's 1, 2, 3, 4, 5 white ones. So here's one way in which we can arrange the flags. Good. Just make it colorful, I guess. So here's the blue, and here's the blue, and here's another blue one. And then we had a couple red ones, red one and red one. Okay, so if we put this up, raise these flags in this color order, someone from really far away can read this message. White, white, blue, white, red, red, blue, white, white, blue. Okay, that means something. They go over to their code book and they can interpret that and figure out that that means something. Maybe this means, maybe this means help or something. They need help, come over. Or maybe there's another set of flags. Maybe another one, it could be that this one is blue, and this one is blue, and this one is blue. And then we have that maybe this one is red, and this one is red. So we have a couple red ones right there. We have a couple blue ones. 1, 2, 3, and the rest are white. So this is another message. Maybe this message means, I don't know, shark in the water. I don't know. So we have different messages that we can convey based on the order in which you put the flags. Of course, see how I didn't put a W here? I mean, like this flag and this flag look identical. So if I swap these, the person from far away won't even know that I moved around a flag. So some of these choices are going to be unique and some of them are not. So how many ways are there for me to make messages that someone from far away can detect? Well, that is this formula. Here we have n, following our formula, n equals to 10. N sub 1 is the first kind of flag, and there's 5 of those. N sub 2 is the second kind of flag, there are 3 of those. N sub 3 is equal to the third kind of flag, and there are 2 of those. Good. Note that n sub 1 plus n sub 2 plus n sub 3 equals to n, right? In our case, this is the 5 plus the 3 plus the 2 equals to the 10. So that all checks out. And so following the formula, we have that it's going to be equal to 10 factorial divided by 5 factorial times 3 factorial times 2 factorial. Right? The number of permutations with some non-distinct items. This will reduce to 10 factorial over, What do I want to do here? Well, okay, let's just use our calculator for this. It's going to get messy. Okay, so now we reach over to our calculator and we figure out what this is. So let's do it one last time with our calculator. So it's 10 factorial, so 10 math probability factorial, there, divided by, and then we have 5 factorial, 5 math factorial, times 3 math factorial, times 2 math factorial. Close parentheses, enter, and we get that. There's 2,520 different messages we can send. Okay. There are 2,520 unique flag combinations that we can send so that people can tell that there's a message, right? Different messages that we can send between boats. Good. Any questions, any questions, any questions? So it's the 10 factorial over the 5 factorial, 3 factorial, 2 factorial, and we get this. So 2,520 different vertical arrangements of 10 flags, given that some flags are identical. 5 white flags are identical, 3 blue flags were identical, and 2 red flags were identical. Good, 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 good. Winning lottery tickets. So in the Illinois lottery, an urn contains balls numbered 1 through 52. From this urn, 6 balls will be randomly chosen without replacement. For a $1 bet, a player chooses 2 sets of 6 numbers. So you get 2 chances to win with $1. To win, all 6 numbers must match those chosen from the urn. The order in which the balls are selected does not matter. What is the probability of winning the ticket? Okay, so here's, for the first time, we're not just counting things. We're going to use those techniques to come up with a probability. Good. Okay, so there are 52 different balls in my pool, from which I'm going to be selecting 6. I cannot select the same number more than once. That doesn't make sense. And the order in which I choose them does not matter. So that, to me, sounds like combinations. The probability of winning is given by the number of ways a ticket could win, divided by the size of the sample space. Each ticket has 2 sets of 6 numbers, so there are 2 chances of winning for each ticket. The sample space S is the number of ways that 6 objects can be selected from 52 objects without replacement and without regard to order. Right? So that's this. It's combinations of 52 choose 6. Right? Remember that giant N means the number of ways. So here is our work here. So N of S, the number of ways to choose 6. Right? This is our sample space. To choose 6 out of 52. It's combinations of 52 choose 6. We use our formula, is this one, 52 factorial over 52 minus 6 factorial, and then there's also this extra 6 factorial there. We could expand it all out and simplify it a little bit, or we can just use our calculator and punch that in. We get 20,358,520 different ways to do that. Again, let's just practice with our calculator and confirm that that's what you get. Right, so we're just confirming that this is what you get when you use combinations. So clear? We end up with 52, math, over to probability, down to combinations, enter, and we're going to choose 6. There. So 20,358,520 different ways to choose 6 balls out of 52 when the order in which you choose them does not matter. And you cannot choose the same ball more than once, right? It doesn't make sense that you would choose the same ball more than once in this case. Good. Okay, so then what's the probability of winning? Well, the probability of winning is the number of ways in which you could win. Okay, you get 2 chances to win in each ticket. That's just the way the lottery was designed. There's 2. You get to make 2 different choices. And then you divide that by the number of possible outcomes from the lottery. Right? You've chosen 2 sets of 6 numbers, and there are 20,358,520 different ways to choose those. So if we divide those, we get this tiny little decimal, right? And then if we move this decimal over 2 spaces, we'll get a percentage, and that'll be the probability of winning. So you can see it's pretty small, right? If we reduce this down, divided this by 2, we would get something close to 10 million, right? This is 20,358,520 divided by 2. So just to show you where they get that 10 million. The 2 divided by 20,358,520. If we divide it, we get 1 over 10,179,260, and they're just saying that that's approximately 1 in 10 million, right? That's where they get this. The odds of winning are about 1 in 10 million. We could also say that it's 2 in 20,358,520, which again we can say about 2 in 20 million, which reduces to 1 in 10 million, approximately. Good. So we want to use all these counting techniques in order to bring them back together and do probabilities. Questions, 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 questions? Okay, I know it's a lot to take in. Section 5.5 is very meaty. Lots of content in there and some really ugly formulas that take a long time to really think through. I tried to present them through the examples of the markers so that we can kind of root them in something and hopefully they made sense. But really spend some time thinking about them. What's the difference between permutations, combinations, and the formulas, and working with your calculator. And then the last section in this chapter is just to bring them all together and think about what types of scenarios would merit one formula. When do you use permutations? When do you use combinations? And sometimes it's kind of both. First you have to do some permutations, and then you divide it by some combinations, and so they could involve a combination of different things. So they get really, really, really tricky. Okay, so make sure that you're chipping away at your homework. Make sure that you read the book. Every page of Chapter 5, there's some great examples in there. So make sure you read them, you understand them, and that you try the homework, and come back next Monday with questions if you have any. So Monday we will wrap up Chapter 5. I'll do the last section. The last section has no new content. It's just a recap of everything in Chapter 5, sort of a quick review and some examples. So we'll take some more examples kind of that require us to use the various techniques we've developed throughout the first 5 sections. Okay. All right, so this would be a good place to stop. Have a great weekend, full of stats, full of math, and I will see you next Monday.